Hello. How's everyone doing? So, I wanted to go over a couple things. Let me share my screen here. So, I kind of wanted to go over, hey Eric, how you doing? I wanted to go over some of at least what I'm doing. And we can go into some of the issues that I had last week. Get a Zybo board picture over here. So in the Zybo board, inside of this chip right here, there is a, draw that a little bit nicer. There is something called the PS region. So this is PS. It's the processing system. So this is where like an ARM microcontroller or an ARM processor would be. So an ARM lives in here. This is where Linux is. Oh, didn't work. There we go. Linux is inside of here. And there's a whole bunch of other stuff too. There could be like SPI controllers. Let's do like SPI. There's other blocks like UART. These are just like controllers to access the outside world, right? I2C. There's one for USB, right? All of these go out of the board, right? Like USB would come out of here, which would be equivalent to USB going out, right? This would be USB. So the reason why I make this distinction is because there's something called EMIO ports, which is extensible multiplexed I/O. So you can choose to route signals like SPI to go out. Like, for example, if I want Linux to use SPI, right? I'd be interfacing with my SPI controller in the PS region. Let's say everything out of here, in this box, I guess. Everything here. Maybe I should just draw this. Draw it here. So this is PL, which is programmable logic. Basically, this is the FPGA. So you can have these SPI lines basically be routed directly out, or you can have them be routed to the FPGA where you do something with it. And if you choose to have it routed to the FPGA, this is where you're using EMIO for extensible multiplexed I/O. So when you set up your FPGA project, you have the flexibility of routing certain signals through certain areas. And this has implications, like this would go out like certain pins. And then these would go out other pins. And if you pass it to the PL, you can sort of do stuff with it if you want. You can like have it be routed to here, or if you want, you can have it be looped back, right? So in my case, when I was testing this loop back here, so it basically you have the SPI controller in the PS region, and then you loop out through MOSI, master out, slave in, and then you get it back in from to MISO. So that's what these blocks would be. This is MOSI. I hate how this, it's sensitive to my hand when I touch the tablet. All right, MOSI. Let's do that. MOSI. MISO. So that's essentially what I did here to test one of the SPI controllers. There's more than one SPI controller, so you can imagine that there's like 2 channels coming out here. Actually, this is a good representation of this because I have 2 SPI channels. This actually is not an OR. This is actually what I'm doing. So I'm routing like these MOSI and MISO SPI lines out. So this could be like MOSI 0, 0. I know it's kind of getting messy. Come on. MOSI 0, MOSI 0. This would be MOSI 1, MISO 1. So essentially this is what I have going on. These pins, this happens to be more specifically the PMOD connector. Even more specifically, this would be PMOD J5. Is this PMOD JF? So that's JF. So essentially I have the processing system and the FPGA, right? Just as a recap, they're both in the sync chip, and then you can output signals out through here. So SPI would basically be going out through here. through this direction here, right? Through some of these pins. And what I was doing prior, the reason why it was not working the last stream is because when these pins are routed out, they are routed, Mosi and Miso were routed to these pins, but I was measuring these two pins. The weird thing about this though, is if you watched last stream, I was able to pick up some data. It just seemed delayed. And what I think that actually is crosstalk that's happening between this signal and this signal when I was getting the data. So I just a reminder, I had these two looped back on a wire, on a jumper connected these two. And I was sending data out from the Zinc processor here. It's just weird that I got some semblance of data connecting these two. So I thought this was a fine path, but it was actually supposed to be these two that I'm supposed to be connecting, just as a test, as a loopback test. I figured that out because this pathway worked. And I was like, well, if this works, right? Like I was looping this back through the FPGA, and I could show you that here. That is right. Where's the... So this is inside of the FPGA universe, right? This is essentially the Zinc block. This is the Mosi and Miso lines. There's a lot more that I could be routing out here, but I just wanted to do a loopback test. So for anybody that is working with these like hybrid systems or these largely heterogeneous compute systems that have like an ARM processor and an FPGA on them, these are very useful tests to do. Like you can loop back peripherals. And, you know, going back to the drawing here, you could do that with a lot of this stuff. You could do that with UART, you could do that with I2C. It's just a really useful debugging technique. So when I looped these back, I realized that this worked when I tried it on the board. So there must have been something that I messed up here, which there certainly was. I didn't have the right jumpers and the right pins. And we can test that. I have the board up and running right now. So let's bring this over here. This a little bit. Okay, so like I said, there's a channel 0 and a channel 1, right? The channel 0 I have looped back on the FPGA. So essentially I don't need to have like any sort of external wiring or anything to facilitate this loopback because it's all happening internally to the FPGA. I said it was channel 0, which I'm using channel 0 there. I'll just say hello, right? Let me maximize this. Okay, there we go. You can see that's exactly what's happening here. TX, I'm sending out the ASCII characters. Hello. These are the ASCII decimal representations of that ASCII, HELLO, and I'm getting that back. We can throw gibberish in there, right? You get the same exact thing. Nothing's delayed. Everything's working properly, right? What I send out is what I get. I'm running at a clock of 500 kilohertz. I should be able to adjust that a little bit. 1, 2, 3. It's 5,000 kilohertz. That looks like that's still fine. 50 megahertz. If I go faster, is this? Yeah, okay. So I'm pretty sure in the Linux driver, there's probably a cap. Like obviously this is not a reasonable speed, right? But there has to be some cap in the Linux driver. So as you're pushing this data out of the SPI controller, it's like, whoa, 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 your speed is way too high, and it probably caps that. This is a really simple Linux utility, SpyDev test. So it's not capping you or not showing you error messages or anything like that. But yeah, this works. And this is for SPY channel 0. This is a testing channel, right? I don't really care about the 0 channel. What I care about is channel 1, because channel 1 is the one that is going out to the PMOD pins. And I do have a jumper on these, which is this right here. I have a jumper right here. So we can go back to the terminal here, and let's test SPY channel 1. Let's do some different content here. Let's do like all A's or something. Channel 1 is this one, and you can see we get the same thing. And just to prove to you, I'm not putting like throwing the wool over your eyes or anything. I can, so I will go over here and I will actually disconnect the jumper. I don't know if you can see this. Maybe I can turn this towards you. Let's see what you guys are seeing. Let's get you a little bit closer. Now there's like a lot of cables here. Okay, so the jumper is like right there. So I'm just gonna disconnect this jumper on one side. So now it's floating. I don't want it touching anything else. Okay, that's fine. So now it's floating. Let's bring it back over here. Oops. And do the same exact commands. There you go. There's nothing on the pin. It's floating high. So we've proven that you can do a loop back here. Yeah, can I explain what I'm doing at a high level, layman's terms? Thank you, I will absolutely do that. Let me connect this real quick. Okay. All right, so the goal of all of this, let's go back to our whiteboard. Let me pull in a, so are you talking about like what I've shown so far, or what the whole point of me even doing this is? Encoder. Whole point. Okay. So I'm trying to find a picture of oh, there it is. Can I click and drag this? Or is it going to do a link? Do a link. I'm trying to get a nice picture here. Okay, there we go. So I have this encoder at my desk over there. And I want to be able to communicate to this thing just to see what sensor output there is. Yeah, where am I in the project itself? Okay, so like super high level, like you see, actually I have cameras right over it, so I can just go to that. Okay, top right corner. Do you see it looks like a motor that's on the top here? Honestly, there's probably a better view if I do this. So this guy right here, there's a couple hoverboard motors. So the whole point of this is like I'm making a robotic quadruped, right? And so basically these are the shoulder joints of this robot. And so this is like a test fixture that I created for this. This is part of its eyes that it would see for the RoboDog. And I already shown in previous live streams where you can do image processing and move these motors autonomously based on what that webcam is saying. And then I have like a laser pointer at the end to point to objects that I put in front of the camera. And that's mostly just to confirm that my image processing is working appropriately and I have the inverse kinematics working correctly, or just the math behind moving these motors and having it point to something based on what it's seeing for image processing. It's kind of hard to see, but there's like a little motor controller over there that's O drive. It can control 2 hoverboard motors at once. The problem that I found out very early on was I was not able to, okay, so there's like encoders built into this. They're called Hall effect sensors. And it's actually pretty clever. You're essentially measuring the pulses. So these are brushless DC motors. They're not brushed. Brushless means that it's essentially working on, it works based off of like magnetism. So like there's pulses that it goes from point to point. And inside of this, there's a sensor, and it's called a Hall effect sensor. And so each sort of click that you go along, this Hall effect sensor is relaying how many like clicks along and the motor. I'm trying to like simplify this as much as possible. Just know that there's something called an encoder where you can measure the resolution of how this motor is turning and how this motor is turning. They both have Hall effect sensors. I ripped these off of a hoverboard motor. Or like, have you seen those like hoverboard things that you stand on and you can go forward and go back? They're pretty heavy duty motors. This is interesting because typically quadrupeds or any sort of like robot dogs will not have something called direct drive, or in other words, like generally they'll have like a gearbox or like a gear transmission to step up the torque. But because these are such beefy motors and they have a decent amount of torque already, you don't really need to have a gearbox, although there's some debate as to whether like, is the weight of these motors worth the fact that you can have something like direct drive? Because when you put everything together and put the batteries on, the chassis for the quadruped, at the end of the day, these might not have enough torque, so I'll have to do a gear transmission anyways to step up the torque for these. Anyways, I'm not there yet. I'm on previous testing, I've realized that the encoders that are inside of these motors are not sufficient. The resolution, like for example, if I go from here to here, right, that's a pretty big jump. And the Hall effect sensors can't go any finer than that. And to accommodate for the jerkiness that I've seen when I control this with the RoboDog, you'll see it like in previous videos, it's like really jerky. It moves around like that, right? And that's because it's going between 2 coils. It's jumping back and forth. And you can actually compensate for that. That's called anti-cogging, to compensate for the jumping back and forth. This is a characteristic of like brushless DC motors. So I can't accommodate for that if I don't have a high enough resolution of an encoder. And the Hall effect sensors have a really crappy resolution. I can't remember what it is off the top of my head, but it's definitely not sufficient enough for like precise robotic applications with this. I mean, after all, it's a hoverboard motor. Like, it was made for having a person stand on a thing and then move forward and move backwards, right? You don't need a lot of accuracy with the encoders of measuring where the angular displacement is of the motor. But for this, you do. And to compensate for the jerkiness that you see in the motors moving back and forth, you need a higher resolution encoder. So that's the whole point of this, is like, I'm taking this thing, the AMS encoder, and it will have a lot higher resolution. Oh, and there's also another benefit to that AMS encoder. I mentioned this before, like, I keep saying absolute encoder, absolute encoder. What is an absolute encoder? An absolute encoder is an encoder that remembers its position no matter where it is. So if I attach this to the motor, and let's say all the circuitry is off, and then I just turn it on for the first time, I will know that I'm at 90 degrees and this is at whatever degrees, right? It'll know it immediately. But there's other type of encoder technologies out there called like incremental encoders, which means that you have to home the motors first to get some semblance of where you are. And then the encoders are basically relative. So once you home it, you'll know where it is, and then you can start counting with the increments of the encoder from there. But, you know, that's not cool. Like, I'd rather have an absolute encoder, because if you're working with the robotic quadruped, you can home the joints. It's just you're gonna have an initialization sequence at the beginning of the robot moving every single time. Like, the robot will have to move like to a certain point, hit its limit switches, understand, oh, that's the limit, and then now start incrementing from there. If you have an absolute encoder, you don't need to do that. It's just you turn it on and it knows exactly where its limbs are at any point in time. So that's another benefit of having an absolute encoder. The point of this is, like, it communicates with SPI, and that's why I'm doing like SPI communication here. I've never worked with this absolute encoder. This is an interesting one. There's a variety of different encoders that you can get to measure the angular displacement of motors. This is interesting because it works off the principle of a magnet. So I have a magnet here, and you're supposed to, and generally you're not supposed to put magnets near electronics. This is weird because you need to do that here. So you put this close to the board, and then you start turning the magnet, and this device can measure the angular displacement of how you turn this, because of there's actually a really good diagram of this. Will this just snap in, or will this give me a link? Sorry, you're not gonna use cycloid drive or some gearbox. I was trying to stay away from a gearbox. We'll see. After talking to several people through like YouTube comments and like other people in the community, when I strap a bunch of hoverboard motors onto this thing, right, like that's just like a shoulder joint. If I put it on like 6 more hoverboard motors, it's probably going to be too heavy, including the battery that I had to put on the chassis, and then the chassis itself, and then any other supporting electronics on there. It's ironic, but the hoverboard motors might not be able to support its own weight because the hoverboard motors are really heavy. I was thinking of maybe like drilling holes in the hoverboard motor, but I don't know how far down that rabbit hole I want to go. I was thinking maybe I might have some of the motors be hoverboard motors and some different, like a mixed motor situation. I really want to be able to use the hoverboard motors, because they're so cheap. They're mass manufactured, and they have pretty good torque. And so if I can get away with using hoverboard motors for like a robotic quadruped, that'd be awesome. Because if you look at like high quality, high torque motors that have like built-in encoders in them, they're really expensive. These are not expensive. This is what I was talking about earlier. So like you'd have, I don't know what it's called. Like I keep wanting to say dipole, but I don't know if it's a dipole. Whatever, there's a special type of magnet where you have, do you know how like sometimes a magnet will like, there's a south and north magnetism to it, and it's like cut in half? This one isn't cut in half, it's cut the other way. So it's cut like through this half and not through the depth half, if that makes sense. So it's a sort of special type of magnet, and because it's created this way, you can turn it and it has a different sort of magnetism, and that is like pretty high resolution when you hold this IC to it. And so I need to figure out a way how to mount this madness to the hoverboard fixture so that I can get that out as opposed to the Hall effect sensors. And the first step of doing that is to communicate with SPI. Or like, right now I'm using SPI on the, it really didn't matter where SPI was coming from. I could have used an Arduino or an STM32 or pick whatever microcontroller, right? So many that can do SPI. I happen to be using the Zybo board as the main brain of the RoboDog. But the fact that I'm using it here for SPI testing is sort of like a coincidence. Like, I don't necessarily plan to have this encoder talk to the Zybo board for relaying motor control stuff, because keep in mind, I showed you the O drive over there. That O drive is it's pretty smart. Like, you can pass in encoder value. Like, it's not just a motor controller. Think of it like, if let me pull this up. I'm going to pull up a picture of an O drive. Sure, this will work. So imagine like this is connected to, right? This is what's happening right now. This is what I have. The USB on here, right? Let's do a different color. There's a USB slot right there, right? And I'm just connecting to it there. And this has a microcontroller on it too. And it has 2 channels for the hoverboard motors. So my whole setup, I mean, this is essentially my entire setup, what you're looking at now, except there's one small difference. Let me get the board motor. Right, so this is like, there's 2 of these. These are connected. Right, those are connected. Those are A, B, and C signals for, keep in mind this is brushless DC, brushless. So it's not like, oh, you have plus and minus. There's 3, it's a 3-phased signal for brushless DC motors. And so you kind of have to pulse them at certain intervals to get the motor to move properly. Where's the actual pins? I think it's right here. These pins here take in encoder signals. So these aren't just, it doesn't show it in this picture, but not only are there the 3 phases here, right? So in here, there's the 3 phases. But there's also the encoder. Those are all like bundled in here. Encoder. And so some of the signals go to here, right? And then some of the signals will go into here for the 2 channels for encoder. And like I was saying, these Hall effect encoders are really bad. They're not a very high resolution. So that's where this comes in. And right now I'm like connecting this to this, or this is what I'm about to do in this stream. If I can get to it, we'll see. I'm almost there though. Like prior to this stream, I had issues with just getting SPY to work because I just wanted to test this. I just wanted to see like how accurate is it really. I see what the data sheet is. I wanted to get more familiar with its characteristics. I wanted to be able to communicate over SPY because it says it can support SPY, right? I think I remember reading in the ODrive data sheet that it can work with this sort of encoder, and I would be able to place it in here as opposed to these. Yeah. Ultimately, this encoder will go into the ODrive. But for now, just for testing purposes, I'm just trying to take advantage of the fact that this chip can do SPY, that I can talk to this. I could have, like I said, used like an STM32 or like an Arduino or something. Last stream, I made a foolish mistake and connected these two pins for a loop back on SPY to test if SPY was working properly. And man, I got partially correct values, and that's what really threw me off. Because if you look at the data that I was getting on the last stream, it looked like I was getting the same exact correct data. Like I was getting the correct, how's that even possible? Like the loopback was supposed to be here, on the white line basically that I have. What did I do? I clicked everything. The loopback signals were sent on the white line. I had the jumper really on the, so sorry, the MOSI and MISO signals were going to these two pins. Like they were being routed to those two pins. But I had a jumper on these two pins. So how is it even possible that I was getting back somewhat correct data? Like when I sent out of MOSI and I tried to get that signal back, I sort of got the correct results. It was just sort of like delayed. Like I had to do another transaction to get that data. And there's like some partially incorrect bytes, but a lot of it was correct. So that's what threw me off. I was like, well, of course I have the right jumper here. I'm getting data that makes somewhat sense, but it was really here. So my running theory is there was crosstalk on the lines in the copper traces because they run very close to each other. So it's just like the magnetism that is between copper traces where you're sending these bytes along the wire, right, inside of the copper trace of the board. And because these lines run very close to each other, I'm guessing that they were influencing each other. And that's the data that I was picking up. So that's what threw me off. It would have been better if I just didn't get any data at all, or like it was held high or something. But the fact that I got partially correct data, I did not assume that my pinout was incorrect. Good question though. Like, if anybody else has any questions like that, please let me know. Otherwise, I'm just gonna be talking to oblivion, like just rambling to myself. Yeah, the real trick here is I really need to figure out so I now that I have SPY working, I need to figure out how I can communicate to this, because obviously it's SPY, right? But that's not the end of the story. Yeah, cool. Awesome, Eric. I'm glad you asked that, because I'm sure everybody else had similar questions. Okay, so what I want to do right now is I want to look up the data sheet for this AS5048 encoder. I'm about to connect this. So I've been wanting to make quadruped, and we're just gonna start with the shoulder mechanism and making the gearbox. Yeah, that's a good start. And making like some sort of test fix. I for the longest time I had the hoverboard motor like mounted on a bracket onto like a table, and it wasn't very good for testing. So I would recommend like making some sort of test fixture like I have over there that made testing a lot easier. And honestly, that test fixture isn't that great either. It would be really cool if I had a test fixture that can I'd have to make some linkage system, but it would be, I've seen like YouTube videos where people make this test fixture where the shoulder joint can move along a rail, and you make some linkage system where it can sort of like hop or bounce up. So you can kind of test out the dynamics and how things are moving. I might do that at some point. I really do want to create a chassis, though. At some point, it worries me that the hoverboard motors are as heavy as they are. So let's bring. Well, I can bring the whole thing. Let's do that. Yeah, I would suggest if you do something like this, do calculations first, like to see how heavy you think things will be, and if you have the properly sized or properly spec'd out motor for torque at least, and how much you need to ratio up the torque with the gearbox. The reason why I didn't want to use a gearbox though was because of backlash. And there's like play in the gears whenever, and also like you're adding more parts to the design, which makes it more complicated and more likely for stuff to go wrong, and more maintenance if a gear breaks or whatever it is. So I just thought it'd be interesting and cool to do like something like a direct drive. And like I said before, they're cheap. These are the SPI communication diagrams. I'm interested. So just because I'm communicating in SPI doesn't mean like, right, there has to be like data sent on the line. And I need to know what that data is. I can't just send hello world text across the line. Yeah. I thought that was a big pro for using a cycloidal gearbox was backlash. Yeah, is cycloidal, is that like a planetary? Oh no, I know which one you're talking about. It's like that weird groovy one, right? Cycloidal gearbox, pretty sure. It looks really trippy as you're spinning it. Yeah. Yeah, I think that's supposed to really help with backlash too. Those are gnarly. I've seen people 3D print those too. I like to mess around with it as well. Yeah, that seems like it would be really good with backlash. Honestly, like if I could probably go back, I'd probably use a smaller motor and mess around with that. But at the same time, like there is some uniqueness tearing apart a hoverboard motor and using that as part of a quadruped. I don't know, that's interesting to me because it's so out there and weird. SPI register map. Okay. So to me, all right, so there's like, for anyone interested, as I'm looking through this, just what's going through my mind. There's a microcontroller that's in this AMS encoder, and there's some address space, right? This is the address space, and here's like some limited control that we have. Like, it's not just a dumb passive sensor, right? There's a microcontroller on board, and I need to communicate with it. And here are some of its features and capabilities. And if I want to access any of these sort of features or capabilities, I need to do so through these registers. Some are just read-only, which is what the access type is. Access is like, can I read or write to those registers? So anywhere where you see an R, that's just a read. Anywhere where you see a RW, that's read and write. No operation, dummy information. Clear error flag. Error registers, all errors are cleared by access. Okay, so what this tells me is that in this register table in this microcontroller, there's probably some error flags, and if I just read from just the act of reading, right? And again, these these transactions are happening over SPI. So when I want to send a SPI packet, this doesn't tell me what the structure of the SPI packet should look like, which I need to find because I need to understand how to construct the SPI packet. These are just like assuming you have a proper SPI packet constructed. These are the registers that you're accessing. And so if you choose to read this register, you will clear error flags. And I would imagine there's probably like error flags in some other registers here. Where would error flags be read? Not use, parity error, invalid error, framing error. Okay, so this is the error itself. So I guess error register, all errors are cleared by access. What this tells me is that this is, if I read address 1, basically, like if there's a parity error and I read the contents of, like, let's say this entire register space from 0 to 13, the act of reading it will clear it. And so if I read it again, it will show up as 0. Pretty sure that's how this would work. I've messed around with similar systems that are clear on read. So if the act of reading it will clear it. But that's good. There's error checking in this, right? So I can see if there's a parity error, command invalid. So if I'm like in my SPI packet, when I send over a command, right, and something isn't working properly, I can read this register and see, oh, I sent an invalid command. Whatever I sent didn't make sense to it, right? Or if like the SPI packet protocol that I'm constructing, if the protocol itself isn't correct, right, that would be a framing error, and I would see that here. Let's see what other features it has. Programming control register. Programming must be enabled before burning the fuses. Yeah, I don't think I need to mess with that. At least I don't think I need to program this. I hope I don't. OTP, register 0 position high, 0 position value high. Okay, I'll need to look more into the data sheet to understand what that is. LSB, that's least significant bits. 0 position, low, high. Okay, 0 position. I don't know what 0 position means, but maybe is this the register that I'm interested in for detecting like what the resolution is? I'll find out soon. It actually might be. So this is like a lower significant bytes and then higher significant bytes. Sometimes when the memory spaces don't have enough, like if it's like, I don't know, 16-bit or something, and they want to go to 32-bit, they'll occupy 2 registers like this, just to get more resolution. If you don't know what that means, don't worry about it. We'll get there when we get there. I need to learn how to, oh, there's magnitude and angle. These seem very interesting. Automatic gain control. This seems to have more than just, you know, like standard reading a resolution encoder, right? There's obviously more stuff going on here. Okay, read command. For a single read command, 2 transmission sequences are necessary. The first package written to the encoder contains a read command most significant bit 1 high, and the address the chip has to access. Oh, is that it? So, okay. So it's a read and then the next command, right? Do they have like they must have like an example, like an example packet to send. I would be shocked if they didn't. Right? Generally, they'll have like some examples on here or something. Oh yeah, and I don't think I said this, but I think it's interesting that I'm seeing I2C here. Can I zoom into this picture? There's MISO, MOSI, clock, slave select or chip select. There's PW. So like there's like other communication protocols, I think, and that's what this is alluding to. I didn't know it was I2C though. I wonder if that's what like A1 and A2 are. Maybe that's what the programming thing is, like if you want to program it for I2C or SPI. I'll have to read more in the data sheet. PWM is interesting. I feel like you're almost able to get a resolution out of this. Instead of using SPI, you can use PWM. But we have SPI working, so might as well take advantage of that. And I think SPI is what the O drive here is expecting. At least I'm pretty sure. I think that's what I read. That it's accepting SPI communication protocol in here. So let's keep going down. Okay, there's like mechanical stuff. Well, that's kind of cool. Huh. Okay, I'm interested in looking at like an example packet. Maybe it's more at the beginning. Oh, is this like, I see. This data sheet, apparently this manufacturer has 2 different products, and they just crammed both of these products into a single data sheet. Oh, my thing's right here. I have I'm looking at the encoder here. I have the A variant, which is SPI. Okay, that's why we saw I2C in here, because it's a similar but different product. It's exactly the same, except it just has like I2C. And I'm not using this variant, I'm using A. So I would have had to have used SPI. Cool, good to know. I'm wondering if it just like outputs PWM without me having to do anything on like register settings. I would assume it would be, right? It's just outputting a constant PWM. That would be interesting to look on a scope. And by the way, as I'm going through this, please ask questions if anybody has anything. Okay, don't care about the electrical characteristics. Okay, let's read more into this. The 16-bit SPI interface, so it's 16-bit, that's the registers that we're seeing earlier. 16-bit SPI interface enables read-write access to the register blocks and is compatible to a standard microcontroller interface. SPI is active as soon as chip select is pulled low. The A variant then reads the digital value on the MOSI, master out slave in input, with every falling edge of clock, and writes on its MISO. Right, that's standard SPI communication protocol. After 16 clock cycles, chip select has to be set back to high status in order to reset some parts of the interface core. Everything that was mentioned here is a part of like typical SPI interface. So it's not like I need to do anything special. It's handled in the SPI protocol. like the SPI controller that's in the Zybo board, it knows how to do this proper sequencing. I'm not using 4-wire. Because the interface has to decode the sent command before it can react and provide data, the response of the chip to a specific command applied at a time t can be accessed in the next transmission cycle ending at t plus t com. Really? The data are sent and read with MSB first. Every time the chip is accessed, it is sending and receiving data. So this to me sounds like okay, I think I understand what's happening here. So let me just confirm before I draw it on the whiteboard. SPI command, yeah, let's look at the SPI command response data flow. Okay, so mostly, so essentially on the other side of this, like on the left side, this would be the Zybo board in our case, for now, for testing. So master out, slave in, master out, master is the Zybo board. So I'm sending a command, right? This is the command on the first transmission. Yeah, and then I get a no op, and then transmission 2 is, okay. All right, this is interesting. All right, this is what's happening. And this is how this chip is reacting. I've seen similar designs like this too. Let's copy this. Let's move this to the whiteboard. All right, so what is happening is, copy all that, just get, let's see what happens. Just copy this. Erase this. Okay, this is what's happening. SPI is it has very tight timing requirements. In other words, like to get some of the speeds that you can expect from SPI, the peripheral device or the slave device needs to be able to communicate like that, right? So if you have, let's say our controller here. I swear, I think I need like new batteries in my pen or something. Let's copy this below. That's not what I want to copy. What if I can let me just take another. I'm just gonna grab another picture here. All right. So what's gonna happen here is out of this pin, let's this here, have the transaction above this. Okay. As you know, right, these two pins are doing SPI. I think there's other pins too. Actually, let me check that real quick. So I myself know what pins I'm using, right? So this was the loopback that we were just doing for SPI. If I click into here, remember there's two SPI channels. So one, I have a loopback internal to the FPGA for testing purposes. The other SPI, you can see those two SPI channels here. And this is like the beauty about like working with a Zybo board or these types of chips is like you can kind of route SPI and I2C and whatever out through whatever pins you want on the Zybo board, right? Or I should more specifically say you can route whatever you want out of the chip. If you make a board, like the Zybo board, they have those copper traces routed to specific headers. So as you know, SPI 0, right? SPI 0 is loopback right here. I do that internal to the FPGA. It's not actually going out of the board anywhere. So that's kind of slick to do some sort of like loopback testing for SPI. There's a second channel, and that second channel is going to the connectors. The right question is where? Where on the connectors is it going? Right? If you look at this, it says MIO. By the way, if you ever see MIO in like a Xilinx or a Zinc design, MIO means multiplexed I/O. It means that it's going from the processor region or the PS region, which is right this region here. It's going from here out to somewhere, out of the chip, out of the ball grid array, out of the BGAs on this chip, and it's going somewhere, right? Wherever the board manufacturers decided to route that signal out to, that's where it's going. It's going out one of the BGAs, just like the pins on the backside of this specific chip. That's MIO. If you see EMIO, extended multiplexed I/O, that means instead of being routed to like the BGAs, it's being routed internally, internal to this chip here. It's being routed to the FPGA. And in my case, I do like an EMIO where I just route SPI, the second channel, the second channel, channel 1 instead of channel 0. I route that to the FPGA and I do a loop back here. So it never goes outside of this chip at all. It never goes out like any of the pins, which is crazy because generally you think, oh, well, you're communicating SPI, right? SPI is a protocol that you send from one chip to another chip. It's not this case, right? Like this is all internal where I'm just doing this loop back here. Why do I make that distinction? I make it because you can see, there's no pin assignment here, right? Because it's not going out to the pin. You don't see a number after EMIO, but you do see a number after MIO. And that means what actual pin number. It's associated with one of the BGAs that are coming out of the pin, out of the chip. And you have options here, right? 10 to 15, 22 to 27, 34 to 39, 46 to 51. What are those signals? Well, those signals it tells you right here, right? So MIO 10 is the MOSI, MIO 11 is MISO, MIO 12 is clock, and MIO 13 is slave select or chip select. So if you're looking at this design, you're like, okay, well, like I can pick any one of these. You have to be careful because if this is a board design, right? Someone has taken the time to put this chip on a PCB and routed specific signals out to headers. You need to make sure that the pins that you intend to use are actually being routed to a connector, right? If I chose to do 22 to 27, who's to say that the people who made the Zybo board are actually routing that signal out, right? You have to confirm this. I happen to know, just from looking at the data sheets, it's MIO 10 to 15. But for anybody else doing this, I think it's a really good exercise to, let's have some due diligence here, right? Let's actually look. This is exactly what I would do if I didn't know where this was going, right? There's a reference manual here. If you go down in the reference manual, right, they show these connectors here, right? PMOD JA, JB, JC, D, E, F, right? What are those referring to? Those are referring to these are called PMOD connectors here. These guys. And you can see on the board right here, right? JA, JB, JC, D, E, F, right? So going back down, you see JF and you see a bunch of Mio pins being routed here. This is free, like this doesn't have to be SPI. Like there's other controllers that you can like multiplex out of those IO ports. That's why this doesn't say specifically, oh, this is MOSI MISO, right? These can be whatever you've mapped them to inside of the FPGA. This is one of the like amazing things about working with an FPGA, right? Is you have the ability to customize whatever you're outputting on the pin. And fun fact, that's actually why they call them like FPGAs, or like these heterogeneous sort of systems that you're working with, right? Where you can multiplex IO. I guess there's other microcontrollers that can do that, not just FPGAs. So maybe I misspoke, but there are more modern designs out there that you can sort of mux the IO, where it doesn't really matter what's on this pin because you can make it be whatever you want. Older legacy products didn't used to do this. It's nice that you see future products do this. It's not necessarily a trade of FPGAs, although FPGAs can do this as well. So, looking at this, this is 13, 10, 11, and 12, right? And that's pin 1, pin 2, pin 3, pin 4. So looking back at this, this is 10 to 15, right? Let me put this side by side. So 10, right? Let me decrease this a little bit. So 10 was MOSI, right? That's pin 2. Let me just like screen grab this. So I have it for myself so I see how things are connected. Okay, so MOSI here, that's Mio 10. So that goes to that one. MISO is Mio 11, and then it goes to pin 3. Clock, right? I need to send, so I'm just looping MISO and MOSI back right now, but we need to send more out, right? Because like you can kind of get away with not using these other signals for a loop back because you're just looping back to yourself. The system sending the data knows the clock rate, so you don't need to send that back because it's the master. The peripheral or the slave is the one that needs to know what the clock is. So we need to route these signals out. We actually care about them. Pin 4 is clock, Mio 12, and then Mio 13. Is up here. It's pin 1. And coincidentally, this is actually what I had connected last week when I messed up. I was listening to clock apparently, or slave select. Okay. I'm going to copy this and let's put this in our whiteboard here. Refer to it. All right, but these are, oh, and then also another thing that might be good to look at is a diagram or just like where those pins are. There should be like a pinout of the PMOD connector. Should have been, right? Am I forgetting that I saw something like that? I just want to make sure like pin 1 is in the location where I think it is. Huh, I'm surprised they don't have this in the reference. PMOD. PMOD is like a standard type of connector. So made by Digilent. So I don't have to necessarily like look at the Zybo board reference sheet. I can just look at PMOD connector in general, and this is like a standard pinout for a PMOD connector. They'll always have like power on the far left side if you're looking at it head on, and then ground next to it, and then 4 signals on the top and 4 signals on the bottom. Okay. So that's what these pins are referring to here. So pin 1, what was that? SS? So pin 1 is SS. Pin 2 was MOSI. And then pin 3 was MISO. And then pin 4 is clock. Make sense? These signals are going to be routed to this in that way, right? And then on this silk screen here on the PCB, I'll like rotate this. Oh, I can. S clock, right? So that one goes to here. SS, that goes here. It's MOSI. This one goes here. This one's MISO. There you go. That's what our pinout should be. Right. So this is that. All right, so I got side rail, but the whole reason why I was talking about this was because we were looking at this data sheet, right? And we see what the communication is, right? So I'll connect this here in a second. How this transaction is going to work is we're going to the command and response are going to be delayed by 1, essentially, or the response to the command. So in other words, if I send a command, this was what I was saying before, where like SPI has a very, very, very tight timing requirement. And this is not just for this Zybo board or for this, right? It's like anytime you use SPI, there are very strict timing requirements in which the peripheral device, in this case, this encoder, needs to communicate to the controlling device, which is the Zybo board in this case. So if the Zybo board is the one sending this command here, right? So this is all of these commands. These are all Zybo. The Zybo board. I'll change. Let's do orange, I guess. All of these are the I should probably do it in the same color, right? All of these are the encoder. the reason why when you send, oh, come on. The reason why when you send a command, why? You send this command here, right, from the Zybel board, you get this response, is because the peripheral can't meet the timing requirement to send the data in a single transaction. It needs to be very, very quick. So essentially you have in this encoder, you are like sensing the magnetism, right, of this magnet. And you have this register table, 0x, 0, 0, 0x, 0, 1. Actually, if I were to be like correct about this, technically it goes up, 0x, 0, 3, and so on, right? This is like the address table. And like you'll have a register space, right, where I mean, this is just memory. This is just a fancy way of saying this is memory, right? There's memory here where there's, let's make this simple. So this is like magnet comes in, the IC reads it, right? Or like you have sensor. This is, the whole thing is this IC, right? This whole thing is the IC. You have some sort of like embedded sensor that's in this thing that's picking this up and then relaying this information over to here. And this is like the content of the data, or like where the resolution is, basically. Like, and in a simplistic view of this, where this fills up a register, right? But the problem is, like, when I request a command, the peripheral doesn't know when I'm requesting the command. And it gives me back whatever is in this memory space very quickly. And it can't, what it can't do is you send a command and then activate the sensor, get the values in, and then push it into this register, because that would take too long, because the SPI protocol needs to be really quick, right? So what's happening here is you send a command, and then what you get back is a no-op, which is what that is here. Because you have to get something. The SPI protocol expects something to come back. And that something is, hold on a second, let me get the data for you. So upon that first command, right, this command 1, you get a no-op back. On the second command, you get response 1 back, and that's what you're seeing here. That's what this interaction is. So when I first learned this, it threw me off, right? It's like, why am I getting delayed data? But it's just because this is how this chip is designed. It can't meet timing requirements quickly enough for the SPI controller to get data out. Basically, SPI needs to be so quick. The peripheral can't dilly-dally around, right? Like, it has to be able to meet these timing requirements very quickly. And so oftentimes it's just going to grab whatever like is in this register space immediately. So that's why things are always like delayed by 1. The first command that you send over, well, there's no data that's being fetched yet. Second command, you get response 1. Third command, you get response 2, and so on and so forth, right? Very good to know. All right, let's go back to the data sheet here. I want to know what this command is that I need to send. Or like what the structure of it is, at least. Okay. Read angle. Is this my example? Do I really just need to send an FF? That might be it. Let's look at what that implies or what that means. I think there's a register table, right? And I remember seeing FF in this. There's no FFFF. There's 3 FFF. I just want to know how many, like, is this just like a 16-bit interaction? So I'm just sending 16 bits at a time? It almost seems like that, right? So I'm sending 2 bytes? Is there like a command byte, or I probably like whizzed by it. Do I need, does the first, I'm gonna look at this more closely. I'm wondering if the first 8 bits need to be FF. I might just do what it's showing here and see if I get anything out. I'll just do FFFF. Unless anybody has any other suggestions. For a single read command, 2 transmission sequences are necessary. The first package written to read command is a read command, MSB -1 high, and the address the chip is to access. Second package transmitted. What is the read command? Read. Read out register. This is I2C. This is I2C. Including okay, so programming it, you can, interesting, you can reprogram the 0 position. That's pretty cool. Program is non-reversible stored in ICs for moments. Oh. Zero position is needed. See. Write command. Read command. Read command. Check answer. Okay, I'm just going to send this command directly and see what happens with this. So I guess I'm just going to send a 3FFF. I was thinking maybe it needs to be like a little bit more advanced, or there's like some like framing protocol in front of this, like a command byte. But I guess it's just the address. No, I'll give it a shot. All right. So I need to make some connections, specifically these connections. So let me do that now. Whoops. Let's move this over. Okay. Let's get you guys positioned. All right, we need some jumpers. Actually, these are a little bit nicer. Let's use like 4 connected. 1, 2, 3, 4. All right. Ready to get my breadboard. Let's move you guys. All right, that's probably good enough. Let me just switch to all right. You guys can see that, right? Yeah, okay. So oh yeah, and I need power and ground to this thing too. All right, and I'll add that in a second. Mostly miso clock chip selects. Yep, this is what I have here. Right, just extending those. I soldered these last stream. Soldered it to this jumper here. All right. This is going to be a little tricky. I should almost like should probably take this out of this rack, but yeah. Let's see if I can get this to work. If I need to take it out of the rack, I will, but let's just try this for now. So the first one was miso. Miso's purple. So miso is pin 3. I'm just going to unplug this USB for now, it's in the way. I said pin 3, right? Miso, yeah. 2, 3. So that was the purple one. Mosi. Mosi is pin 2, which is blue. Clock, pin 4, it's green. One, 2, 3, 4. And chip select. That's 4. 1, 2. Wait, did I mess up? No, chip select. No, the clock was 4. Clock. 3, 1, 4. Yeah, okay. And then chip select or slave select is the first one. Okay. So all of those are connected. Let's get mounted here. Bend this a little bit. Show you guys. You can kind of see that, right? So here I have the encoder. This is going around, going in the PMOD connector there, like we had on the whiteboard. Okay. Make sense? Now I need to put power and ground to this, which I can probably feed from the PMOD connector there. The far left is the one that had VCC. I need to check what voltage was coming out of that PMOD connector though. Let me see. 3v3, okay. So I need to connect it to the 3v3 spots. Another jumper. Oh, I'll need power and ground too. So I need 2. this. That's 3.3. And that's ground. Okay. All right. So this is what I have. I don't know if you can see that. Yeah, just connected to 3.3 and ground. And now I need to connect. So blue was 3.3. Actually, technically, I can feed it into these, which is easily accessible. Let's plug it into this one. So let me just confirm. Yep, 3.3. So that would be blue, top left. And this is ground, which is the second one over. Okay. All right, this is my configuration now. Right, so I have the MOSI and MESO lines, which are all the connectors in the middle, going to that PMOD. And then I have the power and ground, right? Ground on the far right, power on the left, going just to power and ground here. Doesn't matter where I'm getting power and ground from. They all share the same power and ground rail. So I could have used the same connector on the far left, but this was just easier to access. All right, I'm going to turn it on and see if we can get anything out of this. It doesn't explode. Looks fine. This is SSH, so I'm just waiting a little bit for the board to boot. Goes. So let me just grab what I was doing before. So this would be channel 1 that I'm using. So I don't want to do ASCII. Okay, I need to think about what I'm about to say. All right, so I need this to be binary. Let me look up something real quick. Python command. I'm just looking up a reference real quick for the Python command real quick to write to like a file. Okay, so there's nothing in my current working directory. I'm in home root. I'm going to call this Python 3 command So this is like a really quick and dirty way to just write binary to a file. So just call it outbin. So now if I do ls, you'll see outbin. XXD is a hex editor, so you can look at the binary file in here, and you wrote deadbeef, right? If I were just to cat it, look at the contents, it's like messy, right? It's just weird binary characters. So this is binary, right? For anybody who's not familiar. I do this all the time. It's a very nice way to just write binary quickly to a file. But it's not just any binary. We want to write what the command would be, or what our command should be. And I guess, I'm doing SPI here. So I should look at the SPI table, not I2C table. So I'm guessing 3FFF. Let's try that. 3FFF. Right, so now if I do a hex editor out, that's all that's there, 3FFF. Now we would do a SPI command. We can look at the SPI dev test real quick to look at the help. So the device that I want to use, I think 0 was our loopback, right? Pretty sure 0 was our loopback. Yeah, 0 is our loopback here. So we can test this real quick. This is also why I wanted to do a loopback in the FPGA. Let's just make sure I'm outputting this correctly. So instead of ABC, right, like I just write ABC, I get that back. Again, this is through the loopback channel, not to the encoder yet. I need to do channel 1 for that. So instead of this, we want to do an input command. So this is input, and I want to do out.bin. Right. So now you see that what I sent out is exactly what I get, right? This is the beauty of having like a loopback channel for testing. So we know that this is exactly what will happen, or this is exactly what we'll send out of the channel 1, and then we'll see what we get back out of the encoder. So the first command is going to be a no-op, which I imagine would probably be 00. So is the second one something? Awesome. It's great. Okay, 187C. Don't know what that means, but this is doing exactly what we expect. The first command is no-op, second is a response. I would imagine the third one is probably going to be some variation of 187C maybe, or maybe because it's floating. It'd be just some random value. This is great. This is what I would expect, or like generally expect to see, right? Like some content there, but the first one was a no-op. Okay. Let me think. So I guess now, maybe I should put a magnet to it and see if we can get steady values. Let's try that. I might have to, I think I need to bring my keyboard over there, but let's try to get this working. So I'm gonna switch you guys over to Lab Bench and bring my stuff over here. This is exciting. I'm glad that I think I got this working. I hope I did. All right. This is pretty slick because this is like happening through an operating system, right? Using SPI. This is not like a microcontroller to another device. This is like an operating, like a processor, like a Zybo board operating system, a Linux operating system using SPI, talking out. So it's pretty cool. Okay, so let me cut this magnet open. This is weird putting a magnet to an IC. It's definitely a magnet. Sticks to my scissors. All right, let's get my keyboard. Bring it over here so I can start running commands. Need to get a USB extension cable for my keyboard. Bear with me. All right. Okay. All right. So, I'm assuming this is safe if I like drop a magnet on this encoder, like this board. We'll see how this goes. All right. So, can you guys see? Oh, you can't. Let me switch screens real quick. You would want to see. Yeah, let's do that one. Okay. So let me also bring you up a little bit closer to this so you guys can see what I'm doing. Okay. All right. Oh, you don't see that one. It's the other one. All right, let's do that one. Okay. Let's change the cursor to this. Okay, all right. Okay, it should be ready now. All right, so guess trying not to get in your way. All right, so if I like do this here, I'm gonna enter a couple times. Oh, man, I feel like I need like a contraption or something. Ah, this is so hard to like. All right, I'm gonna put my hands. Okay, I'm gonna ground myself. I'm gonna put my ESD strap on. And I'm gonna put my hands on the board, but I'm gonna be like slightly raised above the IC. Just doing a bunch of, I guess, reads right now. I'll slightly turn it. It's kind of bouncing around a lot, huh? I'm trying to keep it as still as I can. Okay. Okay. Huh. I mean, this is binary data I'm looking at. I mean, I know that I need to like, I'll need to bit shift it probably to make sense. Like right now, it's like a digital number. I need to turn it into like an engineering value, right? I need to turn it into a value that makes sense. But even so, I would expect it to be like a somewhat stable number if I'm just like reading it. Or like if there's nothing in front of it, right? Like there's no magnetism. What if I just like put my hand in front of it? I'm putting my hand on the IC. Right, I'll put, what if I'm assuming the IC will hold up to this. If I just rest it on there, I should probably look at the data sheet more or something. All right, fine, I'll put it slightly above it again. It just seems to be bouncing around too much. All right. Let me look at the data sheet again. So I was doing 3FFF. 3FFF. I wonder, if I can find anybody else using this chip or see like examples that they've done. That might be very useful. So here's like an example thing that I'm looking at. An example for the magnetic SPI sensor. Module, Encoder, and it looks like they're using exactly the same address that I'm using. I don't need to have a header on my thing, do I? I don't even think I have. Yeah, I don't even have a thing for a header. This is obviously another, this looks like another board. Tag 5048. Sure. Well, it's good to know that if I ever needed to resort to an Arduino, there's a library for this encoder. Let's see what you do, or let's see what some of the get rotation. I wonder if there's like, maybe instead of reading angle, there's something else that we can read that would be more like, not like the common functionality of like an angle might be bouncing around a lot. So it's hard to tell if this is even like working properly. Maybe let's read a different thing. So I imagine these are like errors that you can read, right? So I shouldn't need to have a magnet over the encoder to read some of these other registers. So let's read some of them now. I guess I have to make binary out of this, right? All right, that out.bin was angle, so let's make a couple binaries. So that was for measuring angle. Okay, let's do Python. Let's do one for. Let's do one for no op. Like if I want to request no op, that was all zeros, right? Yeah, so 2 bytes of zeros. 1, 2. So writing that be no op. Do another one. I'm just making the binary files right now that I'm about to send over. Let's do one for like looking at the errors. Let's do I kind of don't want to mess with programming control because I don't know if things are working properly. So I don't want to accidentally like write to this burning fuses or something. I want to do a safer thing until I know what I'm doing. Programmable customer settings. I just want to look at the read-only ones. Diagnostic plus automatic gain control. Automatic gain control. There's a high magnetic field. Oh, that's interesting. So like I can increase or decrease the sensitivity of when it's reading the magnet. That's kind of cool. That's 3 FFD. That's AGC. 3 FFD. 3 FFD. I'll just put AGC. AGC. All right. So we have our binary files. Let's do no op because that seems the most safe. No. Whoops. No op. So the first one was the previous command, and this one was the current one. Oh, it seems like it was like delayed a little bit because I did it a couple times. Interesting. Well, I'm doing no op now. That's definitely what I would expect to get for no op. I don't know what that was about, where I had to do this a couple times. I'm just expecting it to be lagged by 1. I don't know. Oh. No, never mind. I was thinking maybe I had to like add a couple other bytes here to get the response back or something. You know what, let's try it. Let's try it. That might be viable. So essentially, like, I would send a command here, and then I would do filler bytes here, and then maybe I might get a response back here. The only reason why I sort of like know to do that, or I'm suggesting it if it ends up working, is because I've seen other SPI designs have like a lag to them, where it's like each one of these are being clocked in and on a high, like a rising edge of a clock on the peripheral device. And so I'm guessing maybe it takes a couple clock cycles to read in the command and then a couple more clock cycles after that to give you the response. Or maybe it just gives you the response in the same clock cycles as it's getting in the commands. That probably is it, so this might not help, but I'm gonna try it. Let's do Python. Actually, all right, yeah, all right. I'm hesitating, but let's do let's do that. Let's do that on the angle. Where's the angle one? Oh, I guess I did move to name the angle. So let's do angle here, angled up in, and that was, what was it again? 3FFF? 3F. 3F, FF. And then like, let's do a couple bytes here for like a potential response maybe. Let's differentiate the file. Let's say long at the end or something. Okay. And now let's try angle long. I got something there, but that might be just junk. We do it one more time. It's interesting that it's stable now. All right, now let's do like no op on this. No op long. And then now let's do no op long here. Interesting. Yeah. So this would be from the former response. Remember, everything's lagged by 1. So this is a former response, and this is the current one, presumably. Still testing this out, seeing if this is really how it's working. So I'm going to do angle long again. So that's the no op response, I guess. That's the response. I feel like it doesn't matter. I could have done no op normally. Okay, now I'm going to switch to no op without the long. Okay, do it one more time. Okay. And now I'm just going to do angle normally. So when I do this, it's going to be 0 because the no op from previously is going to be registered, right? So all zeros, we expect the response. Do it one more time. This is weird value. Okay. Because if you saw the other one, it wasn't doing this random jumping. That's exactly what we were seeing before, right? This is like some random jumping. But if you use the long variance, let's do the long again. So no op long. Do another no op long because it's delayed by 1, I guess. I just did it a couple times. All right, let's do angle long. Let's do it one more time. 80. 8000. This seems stable. I'm curious if I started doing angle longs, I would see like values that I would expect to see. Oops. Did not mean to start that. Come on. Oop. All right. Just trying to. All right, putting it kind of on. Oh. Yeah, I'm definitely not picking it up. All right. All right, I'm gonna try a few more things. Let me know if anybody else has any other ideas too. Please feel free to let me know. let's try reading the error. I'll stop doing like the long representation of this. I'll do no op a couple times, clear stuff out, I guess. Let's do error to see if there's any errors. So that one is going to be a no op. Wait, is error? Yeah, error is 1. Okay, makes sense. Do another time. 6000. That means there is an error, right? And if I do it one more time, supposedly, like I was saying earlier in the stream, it's clear on read. So the fact that I just read it means if I read it one more time, what I expect to have happen is it's just all zeros. So that'd be a good way to confirm this is like at least somewhat working. No. Let me do it again. No. Okay. So either my understanding is not correct, or I'm not doing the correct thing here. Clear error flag. Error register. All errors are cleared by access. Yeah, I don't know then. I'm curious. Maybe I have my Indianness flipped for the bytes. Did it say it was LSB or MSB? I think it said MSB, right? MSB. So I think I have it correct. I can try flipping it, but that probably won't work. And when I say like flipped Indianness, I mean like instead of sending a 0001, I would send a 0100. But I think this is MSB. I can try it real quick. I'll try it on the error one, I guess. Oops. I need the Python commands. Python error flip Indianness, and then let's do 0100. Interesting. Something's weird. How am I getting the same thing back when I flip the Indianness? That's just weird to me. I'm gonna do no op to clear stuff a couple times. Oh, it's cool. It's just like stuck at 6 now. All right, I'm gonna try to power cycle it. Hopefully it's not broken, but I'm power cycling everything. So I just power cycled the Zybo board. I'm gonna have to call it here pretty soon. Give it maybe 10 more minutes. If I can't figure it out by then, I'm gonna have to continue this on the next stream. Definitely getting closer though, that's for sure. So I just did no op. Again, I mean, that's what I would expect. Just do an error. Interesting, okay. Interesting, it's just forever 6. All right, what is 1, 2, 3, 4, 5, 6. So that's the 2 bits that are high, right? And 6, 2 bits that are high, 0 and 1. So the reason why I did that is because those bit placements mean something for the error flags. Look at this real quick. For the error, okay, these bits right here, it means something, right? So 1, 1 means command, assuming that I'm getting a correct value back. It means the command is invalid and there's a parity error. Interesting. What? The command is invalid and there's a parity error. Is there a wrong way of how I'm commanding this thing? I'm gonna look at previous or other examples online. Data to send. Okay, what is the data to send? This was the Arduino example that we were looking at earlier. Okay, they bitwise OR this with data. Bitwise OR this with shift it to the left F. Draft another packet including the data and parity. Ooh, okay. Interesting. All right, so, okay, all right. I'm gonna attempt to do that. All right, I'm gonna open up another terminal. All they're doing is shifting it to left by F. So let's look at this real quick. So if I want to send 0x3FFFF, no, 3FFF, right? They're shifting it to the left by 0xF. Sorry, it's, and then let's view this in hex. Is that really what's happening here? Am I really sending that out the wire? Sending data to right. They do shift to the left. Oh, but they're doing something here. Spy calc even parity. Where is that? Value ANDed by 1. Oh, okay. Split function is to calculate even parity. So I would have to take the value and by 1. And is this the value shifting to the right by 1? I see what's happening. So you're going through the bits and counting the high bits. Yeah, you're counting the bits that are high. I wonder if there's a Linux utility that does this. Let me look. Is there a Linux utility that calculates? You could probably ask ChatGPT just to do it real quick in Python or something. Can you write a Python command that, let me see what they're doing here. That will calculate the even parity of a 16-bit value. Cool. All right, so parity is a way, I think, to it's to understand if it's all about data integrity, the data that you're sending over. So I'm assuming that the encoder expects to have some parity bit that's set, and it looks like this Arduino library is setting some parity. So basically the data that's being sent over, it can't just be that. I need to also send a parity associated with that data, and that gets sort of like amalgamated into the data. You'll see here what I mean in a second. But this should work. This is like a quick, nice way to do it in Python real quick, and it spits out the parity number. So let's go over here and let's say like I want to calculate 3FFF. Oh, invalid syntax. Why? What is wrong? Import sys. B equals int. Why is that invalid? Could it be that this is like an ASCII character and not actual ASCII? Is that what I was using? No, I was using count before. Okay. Still doesn't work. Come on, give me something that works. Yeah, all right, it's gonna, oh. I'm dumb. It's because I was actually in the Python interpreter. There we go. So what if I do 0, 0, 0, 0? 1? Okay. 0, 1. Okay, so let's try this. So what it was saying was, this is kind of like manual and tedious, but I just want to make sure that this is working right now. So now that we have the parity, right? Just to recap, I'm just trying to figure out how to transfer data successfully, right? And I think part of that is you need to send a parity bit with the data. So this Arduino library looks like it was taking the data, whatever that may be, right? So this is the data to send data. If I trace this back, you know, if I look up write, or like look at anywhere where there's a write in here, I imagine that like they'll have, let's see, the other writes in here, right? So these are just highs and lows, so zeros and ones. Just want to write 0. Digital right. I want this right. All right, I'm assuming that this is correct. So like this is the data that I want to send. So this would be like 3FFF. but it's being passed through this parity calculation. And it's being like shifted to the left F and then ORed with the data. So it's like, if you don't know what bit shifting is, it's like a whole subclass in itself, but like I'm just amalgamating this content into the data already. Okay, so if I were to, so let's say like a 3FFF, right? This would be 0, so that means this value would actually be correct to send this over. But what if I were like, that means like I don't have to, I could just send 3FFF and it should be just fine. But 1, there's a parity bit of 1 there. So I'm assuming, and this 1, if I shifted it to the left, F, right? 1 shifted to the left, XF. Eight, 0, 0, 0. And then I need to bitwise OR that with the data, 0x0001. Oh, because it's in hex. Let's just get rid of the hex. Let me put hex around all of this. So that would be the actual data. Essentially, you're taking 1. Like if I were to put this in binary, it would probably make a little bit more sense. And this would be like shifted to the left. F, 0x0f is the same thing as saying 16 decimal, right? So this is the same as saying, take the data that you want to send and bitwise OR it with 1 shifted to the left 16. So if you count like how many bits this isn't binary. This would be 1 shifted to the left 16, right? But this is the original data that we want to send. But we want to send all of this because we're sending parity. So it's like I said, it's like you're amalgamating the parity bit in with the data, which is what this looks like. So essentially it's just a, if I were to represent this in hex, it would be 8001. So let's do that. So for air, oh, sorry, I'm not in my shell. So let's go here. Let's do another Python command. Python. Oh, because I just rebooted. That's cool. Python. Okay, let's do this. So we would want to do 1, but then 8 up here because of parity. So this would be air parity. Okay. Spite of air parity. There we go. Well, it's something else. All right, and that's clear on read. Okay. So 2002. What is that? In binary. 2002. So the second one, I. Command invalid. But then it got cleared. But clearly, like, all right, I think that this is the right track, right? If I did a no op, 0, 0, and then I read error, there are no errors. But for 3FFF, right, which is the thing that we were reading before, it's a 0 parity. So I should be able to just read angle bin. I'll do one more because the command's lagged. Interesting. Do it again. I don't know why I had to do it an extra time. Then let's do an error to read if there's like errors. Oh, okay, that's lagged. Is it lagged by 2? 16d6. Is my clock too fast for the device? I wonder what clock speed. Clock speed. Ooh. Max is 400 kilohertz? Oh no, that's IGC. Time between last falling edge of clock and rising edge of chip select. No. Serial clock speed. 100 nanoseconds. That is 100 nanoseconds is 10 megahertz. It should be okay. It's not going super fast. Do angle again. Angle third time. Error parity. Angle, error parity, error. But to me, that looks like there is no error for the angle that I'm reading. Oh, maybe it's bouncing around wild like that because it's calculating the parity. So I need to remove the parity bit, because it probably is sending me parity as well. That may be what it is. Okay. I need to write a better application for this. I need to write like a Python application that will allow me to do this a little bit easier and to calculate parity and send parity and like get data back and then remove the parity bit. Because the data that I'm getting out of this, it may be correct, but I'm just getting the parity bit. So it'd be nice if I could just run this super quickly and remove the parity bit as I'm getting the data over. Because this may not be the actual, like, right, I need to make some augmentation to this data because of the parity. I'll try that next, but I think I'm gonna end the stream here. This is a good stopping point. We made a lot of progress because 1, we fixed SPI. SPI is working. 2, we have a loopback on SPI, which is great. We did all this stuff. We connected all of this, and we're looking at the characteristics of the SPI signals back and forth. And we're getting some data out, some reasonable data. It seems to be making sense for the most part. And I think we just figured out why it's sort of like having this sporadic behavior with reading the angle. I think it's because of the parity bit, so I need to remove the parity bit from that. So good progress. I'm gonna end it here though. So thank you everybody for watching. Appreciate it. See you guys later.